legacies of glorious traditions, where folktales are regarded as guidebooks to perfection, honed over centuries, yet possible to experience within a few hours. Experiences you can take home. Here, art preservation is a tourist attraction. History is a living monument. Even shopping is meaningful. See world-famous resorts compete with local means of accommodation. Enjoy natural kindness. Or the excitement of exploring nature. With endless stories to tell and never-ending feasts. Never-ending possibilities to get more out of life and journeys. Yogyakarta. Wonderful.
Indonesia.
A wondrous civilization. Disposed to tranquility. With scenic landscapes bordered by the sea. Here, mythologies become principle. And religions create the cornerstones of life. It is contained in the arts and crafts, where celestial ceremonies become part of popular culture. Legacies of glorious traditions, where folktales are regarded as guidebooks to perfection, honed over centuries, yet possible to experience within a few hours. Experiences you can take home. Here, art preservation is a tourist attraction. History is a living monument. Even shopping is meaningful. See world-famous resorts compete with local means of accommodation. Enjoy natural kindness. Or the excitement of exploring nature. With endless stories to tell. And never-ending feasts. Never-ending possibilities. To get more out of life and journeys. Yogyakarta. Wonderful.
Indonesia.
A wondrous civilization. Disposed to tranquility. With scenic landscapes bordered by the sea. Here, mythologies become principle. And religions create the cornerstones of life. It is contained in the arts and crafts, where celestial ceremonies become part of popular culture. Legacies of glorious traditions, where folktales are regarded as guidebooks to perfection, honed over centuries. Yet possible to experience within a few hours. Experiences you can take home. Here, art preservation is a tourist attraction. History is a living monument. Even shopping is meaningful. See world-famous resorts compete with local means of accommodation. Enjoy natural kindness. Or the excitement of exploring nature. With endless stories to tell. And never-ending feasts. Never-ending possibilities. To get more out of life and journeys. Yogyakarta.
Frederick, are you there?
Yes, I'm here. Can you hear me?
Okay. Okay.
Good.
So I think Michael also already in here. Hello, Michael.
Yes, hi.
Okay, thank you. So I think the moderator will be Saiful. Saiful is already here also. We are waiting for 5 minutes. Pak Saiful. Thank you. And maybe I will mute all of the participants, only the speakers. The moderator can use the microphone. So this is one way to avoid the noisy, some kind of, we don't want to hear about. So hopefully everything will be okay.
Thank you.
Microphone oke ya Pak Saiful ya?
Tes Pak.
Oh,
Dengar Pak ya? Ini pakai laptop rumah ini Pak.
Oh, oke.
Mudah-mudahan lancar.
Ya. Huh?
Acara.
Silakan dimulai, Pak Saiful.
Ya. Selamat datang Bapak Ibu sekalian peserta webinar. Mudah-mudahan bisa mendengar suara saya ya. Before we begin the webinar, I would like to request your attention, all of you here, to the following protocols. First, this webinar will be conducted in English, and the discussion question will be held at the end of the session. So you may use the chat as well. I believe you know. You all know how to use the chat in the Zoom, and the certificate will be available. Please sign up at the link given by the organizers, and the material of presentation will be made available for you, and you can request to the organizer via the email. Okay, representative from the International Atomic Energy Agency, IAEA, colleague from the Indonesian Nuclear Society, representative from National Nuclear Energy Agency or BATAN, distinguished guests and participants from ministries, nuclear agency, regulatory body, industry, university, ladies and gentlemen. Welcome to the international webinar on the readiness on high-temperature reactor. Today, Tuesday, 8 September 2020. This webinar is organized by Indonesian Nuclear Society and International Atomic Energy Agency, or IAEA, as a series of webinar activities toward the HTR 2021. And this webinar is aimed to first to provide the information and current status of HTR 2021. Second, we like to provide an overview as well of HTR conference and the current status of HTR R&D, or research and development here, construction plan, and the operation in the near future. And finally, we would like to promote the interest as well of to the nuclear communities and wider audience in HTR 2021. So, distinguished guests, colleagues, ladies and gentlemen, we have 3 speakers today. The first one is Professor Dr. Jarod Sulistyo Wisnubroto. He is the chair of HTR 2021, and also he is the previous chairman of BATAN 2012 until 2018, if I'm not mistaken. Is that correct, Pak? Hopefully it's correct. And then secondly, we have the Michael Futter here. He is the co-chair of HTR 2021, the employee of Joint Research Center, European Commission, Belgium. And we have the third speaker here, Fredrik Ritsma. He is the co-chair of HTR 2021 as well. He is the team leader of SMR Technology Development, Nuclear Power Technology Development sections on the IAEA. And we are hoping that you can enjoy all the 3 speakers today. Before we start, let's move on to the first speaker today. I would like to invite Professor Jarod to deliver the presentations, as well as giving the welcome remarks to the first webinar of HTR 2021. Professor Jarod, floor is yours.
Thank you, Pak Saiful. Good evening in Jakarta, Indonesia, and some part of Asia and Australia. Good afternoon, our colleagues in Europe and other part in Middle East. And also good morning for our colleagues in American zone. My name is Jarod Wisnubroto. As a representative of Indonesian Nuclear Society, I would like to say welcome all of you in this first webinar towards HTR 2021. For Indonesian Nuclear Society, this is not the first one. This is the 16th webinars. During 3 months, we already conducted several webinars. Some topics are including the SMR technology. 2 weeks ago, we requested the Russian to discuss about the floating NPP. And a week ago, we invited a professor from Tsinghua University, Professor Sun Yu Liang. He speak about the HTR development in China. It's very interesting. So many audience ask about this generation 4 HTR PM that soon will be in operation. He said that before the end of 2021, that HTR PM will be in operation. So now we have the first webinar for the towards HTR 21. Maybe some of you, some Indonesian have a questions why we consider of the or we are interested in this international conference of HTR 2021, because we believe that Indonesia as a big country, someday we will use the nuclear power plant, but someday also we use not only one option of technology, maybe pressurized water reactor, maybe also the other technology, including high temperature gas cooled reactor. Why? Because some remote areas, some part of Indonesia need they require not only electricity, but also the heat for the industry. That's why this is one thing that we should continue to learn to study this HTGR technology. So I would like to show you some short of my presentation. So the title of this first webinar is High Temperature Reactor Readiness in the World. I think this is very good to, well, for the audience to know about the readiness of this technology. I think Michael and Frederick will explain deeply about this kind of technology. Pak Saiful already mentioned about what is the objective of this first webinar. As you know, we will, well, originally we would have the International Conference of High Temperature Reactor 2020 in October this year. But due to the pandemic, we postponed that event. We moved to the next year on June. During, well, waiting for the next year, we initiate to conduct the webinars. Maybe this year, not only this webinar, maybe there will be second webinars. Then next year, we also have another webinars. But it is possible also if the audience, especially this young student, want to learn more about high temperature reactor, maybe we can invite expert from outside, from abroad, to give the special lectures on this kind of technology. And this webinar aims to maintain the momentum of the conference, and we can interact and engage with all of the participants of the international conference. And more than that, this is very important, the webinar also serves as a promotion of high temperature gas cooled reactors, especially for young generation, everywhere, not only in Indonesia, but also in the world. So I would like to talk about the international conference. The total registered for this international conference, 217, but due to some reasons, some of them 15 withdraw from the conference. The remaining is 203. And the participants of this international conference, mostly from Indonesia, they submit the abstract. Totally from Indonesia 79, and then China 54, United States 20. Well, I have to move this. Oh, sorry. Then Poland 9 and other countries, totally about 17 countries. So this is the situation of the registered person in the next year high temperature reactors conference. This is very important for the audience who participate in the next year international conference. There are key deadlines: full paper submission, well, several days ago, August 31st, and the review notification October 31st, and final paper at the end of this year. But some participants, because maybe, well, the pandemic, they have to work from home, they cannot go to the office, they cannot go to the laboratory, they ask us, the committee, to extend to submit their full paper. But it depends on the case by case. But hopefully also we expect there will be no, well, delay or have to change the timeline. Up to now, the paper submission is totally 84 papers. So this is the topics of the international conference, from the National Research Program and Industrial Projects, Industrial Application and Markets, Fuel and Waste, and then Material Component and Manufacturing, Reactor Physics Analysis, Computer Codes and Analysis, Development Design and Engineering, and Safety and Licensing. I think there are several submitted abstract that's very popular in the track, the conference called the topics track, fuel and waste, 36 abstracts, and then the reactor physics analysis are 38 abstracts, and another one is very, well, there are some people, submitted the abstracts on the development design and engineering, 38. So what kind of publication of the papers? First, we will publish the conference proceeding, published with ISBN. And the second, this is usually for Indonesian, usually the Indonesian young or junior researcher want to be promoted as a senior researcher. They are required to have papers that published in the Scopus Index Conference series. So we will also, for those interested, the papers can be published in the Scopus Index Conference series, well, with the additional fees, $100 US. For the selected papers, around maybe 30 up to 50, the best papers, it depends on the reviewer or track leaders, to be expanded and published in Elsevier Journal of Nuclear Engineering and Design. And there is another option also for proceeding publication in IEA. So we also want to conduct the youth competition. The key deadline, abstract submission, August 31st, selection notification in middle of September, and submission and announcement of grand finalists at the end of October this year. This is the title of the youth competition's participants. There is one from China, one from Poland, and 9 from Indonesia. It's very interesting. The young generation, they submitted some thema like HTR Quizline, functional simulator of Yogyakarta reactor operating control system, nuclear play and pop book and busy playboard for nuclear education, RDE, the beginning of green and versatile power plant. Even someone submit it's very interesting, the utilization of augmented reality or AR capabilities to create quiz filter on Instagram to enhance youth's interest in reactor technology. So we also have a space for industrial exhibition. So we request the industry, the vendors, or another or private sectors want to use this opportunity to have exhibitions, or maybe the National Nuclear Energy Agency, Batan, maybe want to show their product their technology, Batam can also use this space of the exhibition. So this is my presentation. If you have questions regarding the international conference, you may contact through our email, the contact at HTGR2020.org, or if you want to know more about this conference, you may visit our website, www.htr2020.org. This is my presentation, Pak Saiful. Thank you very much.
Thank you so much, Pak Jarod, for the presentation. Talk about the status of HTR 2021 and the track division participants, as well as the youth competitions. For the second presentation, today I would like to invite the Michael Frutter. He's from European Commission. Frutter, are you there? Michael?
So now it works.
Yes.
Thank you for
it's your time, Michael. Time is yours.
Yes. Thank you so much. I was muted and couldn't intervene.
Okay.
So thank you for this introduction. I'm pleased to share a few slides with you, which I'm trying to do now. So I hope you can see that. Please confirm. Can everybody see the slides?
Yes.
Okay, excellent. So yeah, thank you. I wanted to give you some background to the HTR conference series and explain you why I think it's so
Michael,
interesting.
sorry.
Michael?
I think that you have to click the second from the right one.
You have double
below.
windows over there.
Yeah.
Show
For the
us.
full screen.
I show the full screen. Wait, you have what you have? You mean this here?
Yes.
I work on two monitors, so that's why I don't know which one. Hold on. Sorry for this.
You may shift the second monitors, I think.
This.
Well, I think you can click the three dots, the right one, yeah. Then
Yeah.
hide presenter view.
Oh yeah, I see.
Yeah, okay.
Oh, you're
excellent.
So this is only my second experience with Zoom, so I thank you for doubling my experience already. So again, so thank you for the introduction, and I wanted to give you some background to the conference series and why I think it's so interesting. Why am I qualified to talk about that? It's because I'm the vice chair of the International Organizing Committee. I work at the European Commission's Joint Research Center in Petten, the Netherlands. And why do I tell you that? It's because Petten is the place where it all started. I come to that in a minute. This is the summary of my talk. It will be even shorter because Professor Vishnu Broto has already talked about a couple of things. But I wanted to share with you a little bit more detail, for example, on the topics and the tracks here. So you have seen that they were already mentioned. We have the 8 classical tracks. You see them also on the website, and every track has an international and a local track leader. And I wanted to introduce them to you because I think it's important that these are not just anonymous tracks or letterboxes, but there are people behind it. So in the first track on national research programs and industrial projects, we have Frédéric Reitzma, who will talk after me. He's with the IAEA, and Genirina Sunario from Batam. So we have, she's the local track leader, and Frédéric is the international track leader. So I don't go into the details. This is the subtopics that you can expect in that track. In the second track, industrial applications and markets. So that's my responsibility, and Sriana from Batam again Here we talk about heat applications, for example, industrial process heat, hydrogen, desalination, things like that. In the track fuel and waste, we have as a track leader Paul Demkovich from INL in the US and Bing Liu from China, together with Ratiko from Bataan. We have 3 track leaders here because it's really a big track, as you may have seen from the numbers of papers. And here we talk about everything regarding fuel from the beginning, from the manufacturing to waste management. In the area of materials, components, and manufacturing, that's the next track. The track leader is Manuel Pouchon from PSI in Switzerland and Ridwan from Bataan. Here we talk not only about metals and their properties and performance, but also on ceramics and graphite and their behavior under operating conditions, including corrosion, irradiation effects, and things like that. We also scale up to component design for things like circulators, hot gas ducts, steam generators, heat exchangers, and things like that. And then also very important, oh, sorry. Something happened here. Can you see the slides?
Yes, we can see.
Yeah, I'm sorry, I hit the wrong button. So very important also, we do the modeling and simulations because we want to end up with valid design codes and standards. So that's, I think, a very important track here. Reactor physics analysis, again, a very big track here, led by Frédéric Damian from CEA in France, Jim Kuiper from Nuclic in the Netherlands, and Alexander Agung from Indonesia. And here we deal with nuclear data, the modeling, the simulation, the computations, and then for the full core analysis and also the fuel cycle analysis. So, so not only the analysis itself, but also the methods and the codes that are involved in this. Then specifically for everything else, we have a specific track on other computer codes, which covers thermal hydraulics, structural mechanics, multi-physics analysis. And here responsible is Li Fu from INET in China and Topan Setyadipura from Bataan. And here we, yeah, as I said, we talk about thermal hydraulics, the methods, code, heat transfer, accident analysis, structural analysis, multi-physics. Specifically for HTGRs is fission and activation product transport and also vibrations, very important for the operational analysis and sometimes even for licensing. We have track 7, development, design, and engineering with Xin Yan from JEA in Japan and Mohamed Soubekti from Bataan as track leaders. And here the topics are progress in new generation reactor designs, plant dynamics and control, system and facility design, economic assessment, construction methods and experience. So all very practical topics for which we are very happy to receive feedback during the conference. And then if you want to build new reactors like SMRs of the HTGR type, then very important is the chapter safety and licensing. Responsible for that is Farshid Charoki from Framatome Inc. in the US and Budi Roman from Bapeten in Indonesia. Here we talk about safety design and analysis, accident analysis, seismic analysis, source term evaluation, safety concepts, and all the ways that are necessary, the strategies and methods to go through licensing processes, which are different also from one country to another. So the conference we wanted to hold in October would have been number 10 in a series that started in 2002 in Petten in the Netherlands. I said it already, so that's the that's where it all that was where the germ was planted, basically. And the reason was that from the contacts and the networking we have done in Europe with the US, with the Russians, with China, Japan, and also South Africa, we have found out that there was really a great and growing interest in HTGR technology worldwide. And so we decided to bring the most active experts together in, well, what was looking like a workshop initially. And then initially and immediately, in fact, afterwards, in 2003, we wanted to hold the next conference in China, but already that was the first time that the conference was delayed by a pandemic, which was SARS. So in 2004, in Beijing, this was the delayed date. The conference has become really big already. We had, I think, 500 or more people there already, because China had a very strong program. And so after Beijing, we kept the biannual schedule and moved in 2006 to Johannesburg, because in South Africa they had the PBMR project, which was very much advancing at that time as well. And in 2008 we had the conference in Washington, just under the eyes and ears of decision makers in the Senate in the US. In 2010 was Prague in the Czech Republic. Remarkably, in 2012, we went to Tokyo in Japan, just after Fukushima. So this was a very nicely done event, even though we had all this, aftermath of Fukushima to deal with. In 2014, Weihai in China was very interesting, because this is, for those who know about it, the place where the Chinese built HTRPM just now. So it's in the final stages of commissioning, and we expect it up and running in the course of next year. In 2016, we were in Las Vegas. In 2018, in Warsaw, because Warsaw, Poland, is also now moving on to HTGR development and has been running already several projects. And then, out of laziness, we decided to just turn the flag around, as you can see, and we moved from Poland to Indonesia. And Batan has offered to hold the conference in Yogyakarta now in October, and unfortunately, due to COVID-19, we had to move it. So you see from this that there was mostly a rotation of continents involved. We had the conference often in capital cities, not systematically, every 2 years, and it lasts typically 3 days. We are organized in an international organizing committee and a local organizing committee, and the link between the two is the chair of both, because the local organizing committee chair is for 2 years also the chair of the international organizing committee. So the local organizing committee changes every 2 years, because the conference venue changes, and they take care of the whole preparation of the conference, including venue, accommodation, travel, and so on. And then the international organizing committee is more of a permanent nature. So I'm the permanent vice chair. Currently, at least, there are 36 permanent members from 4 continents and international organizations, and we meet usually in person at the conference. So in terms of impact, why do I think that attending the conference is useful and important? We have seen from the past experience that our attendance ranges between 200 and 500. That really depends on where it is held, and if the host country is running a considerable HTR program or not. So in any case, what you can count on is to meet scientists and engineers in all stages of their career development. They come from industry, from consultancy companies, from startups, from international organizations, research labs, and academia. But you can also meet politicians there, the press, investors, regulators, a lot of students also. So we were assumed last time in Warsaw to be a group of old people, and the exact contrary was actually true. So I was very pleased to see a lot of interest from the young generation, and I really hope that this will be maintained. And then, I said the host countries often have a strong active HTR program in different stages of development, and that makes, I think, that gives a particular drive to the conference. And as Professor Vishnu Broto mentioned, there's in many cases also an exhibition, which is not only there to make money, but also to meet representatives from companies and organizations that have significant experience in the subject. And of course, I mean, as so many people are there are also numerous side events and meetings. So that in total, I mean, if you hold such a conference, you can count with 10 days of technically related events and meetings on the spot. So this is what we account with. Concerning publications, that's important for scientists in particular. It's important that the conference papers are peer-reviewed and you can get a certificate for that. The proceedings are issued with an ISBN, so this is also why we ask you for a copyright transfer form, and the track leaders, they will select the 50 best papers for further elaboration, review and publication, nuclear engineering and design. And we are happy to have the editor-in-chief of nuclear engineering and design as a member of the International Organizing Committee. So that's Yassin Hassan, Professor Yassin Hassan from Texas A&M University in the US. Then in many cases in the conferences, we had awards distributed to best papers, best presentations, but also to best young contributions. So this depends a little bit on the local organizing committee. There's a lot of freedom there. And yeah, I'm happy to see that Batan is also planning to have that, to continue this tradition. So with this, I'm really looking forward to seeing many of you in Indonesia next June. And I really hope that there will be very interesting presentations and discussions, also not only the papers, but also the side discussions. I think the personal contact, we have seen this now during the pandemic, is something which is extremely valuable. And I think we should cultivate not only through webinars, but really also by meeting in person if we can safely. So thank you for your attention, and again, see you soon.
Thanks a lot, Michael. Very nice presentations. Talk about the importance of HTR conference, the impact, and the tail tracks, 8 tracks from National Research Program to the safety and licensing, and as well as the history of the conference from 2002 until next 2021. Let's move on to the third speakers for tonight. We have Frederick Ritzma. He's the co-host the HTR 2021, as well as the team leader of SMR technology development of IAEA. And we'll talk about the more technical in the session, the status of its R&D and HTR readiness in the world. So Ritzma, time is yours.
Thank you very much. Just to make sure, can you see my presentation full screen?
Yep.
Thank you for the opportunity. Welcome to everyone. I scanned through the participation list and recognize a lot of familiar names. So thank you for the support for the conference and also for this information sharing on high-temperature gas-cooled reactors. So you heard a lot on the conference already, but from my side, I just want to also mention why the agency are actively supporting the conference and therefore also put our name to it. So the conference is also arranged or organized in cooperation with the agency. So this is really the main conference that focus on HTR technology and the different areas as Michael have presented, taking place every 2 years. And I must admit, I checked when we went through the list, and I'm happy that till date I've been to all the conferences. And I must say, it's really been the best experience of any conference I've been to really meet with all the different experts of the young generation, all the local excitement every time as we travel around the world. So it's been really, very good. This, of course, is a very good opportunity from the agency perspective also to engage with the member states. Specifically for Indonesia, of course, it also facilitates the exchange of information on HTRs with the various national stakeholders from government, industry, the regulatory body, industry and academia and so on, the young generation. And also important, as I will later show, it's also recognition, and we can also showcase the activities the IAEA have through the technical cooperation, specifically supporting Indonesia and other member states in the area of high-temperature gas-cooled reactors. So then I was asked just to give a bit of overview on high temperature gas-cooled reactors. I think most of you, or many of you, would be very familiar with this material, but I think it's good to set the scene and for those participating that maybe is not so familiar with high temperature gas-cooled reactors. So we often hear about very high temperature gas-cooled reactors as being pursued by the Generation 4 initiative, or just high temperature reactors or high temperature gas-cooled reactors. So a few areas I want to look at the characteristics, maybe some of the R&D areas, and you'll see it links very well with the topics of the conference. Something on the IE activities, specific topic, a few slides on the flexibility of applying HTGRs, not only for electricity, something about the member state interest, and then to conclude a bit of the information on the last 7 years of support to IAEA, specifically on high temperature gas-cooled reactors through the technical cooperation mechanism. So the characteristics. So this is very familiar. The main thing that distinguish high temperature gas-cooled reactors from other reactors are really the use of this coated particle fuel. So that's a main characteristic. And this is then supported by high temperatures, so typically 750 degrees outlet temperature of the coolant. Coolant being used as helium. All cases is graphite moderated. And all of them qualify as small modular reactors because electricity generation will be less than 300 megawatt electric. So the maximum design being proposed today is only up to 600 megawatt thermal. So really small compared to the current large reactors deployed. Modular reactors really comes from the multiple modules to be deployed, and is really a term that was already in the late 80s pursued by the HTGR community. Other characteristics are really the very low power density of say between 3 and 6 watt per cubic centimeter, and this is typically 10 times to 30 times lower than for current large light water reactors. That brings particular benefits, but also some disadvantages, as I will shortly explain. And we typically have the two families of high temperature gas-cooled reactors, being Prismatic and the Pebble bed design. So as a moment, if I look at what a typical Prismatic design will look like, or we also say block type reactor. So of course it used the same coated particles mentioned before, but this is then placed in compacts that can either be in a fuel rod or directly being inserted in channels within a graphite block. So basically you can get these rows or pins of coated particles with a filler being introduced into the block, and then you can stack several of these blocks high and in a different configuration in a modular design, from small, maybe cylindrical core to a small annular core to a large annular core for different sizes of reactors and different powers of reactors. So this is typical block type reactors. And then the Pebble type, same coated particles again, but this time it's introduced into a billiard size ball or sphere with a small region outside not containing these coated particles. And then we need to put hundreds of thousands of these pebbles within the cavity of the reactor to form the core. The advantage of the pebbles are that they can be circulated, they can be handled online individually, and therefore being circulated through the core in a pebble bed reactor. There's different options. You can also let them only pass one through, but there's variations. But the main thing is that you have a small entity that's easily to handle and that you can do this online. So these are the two main families. Some of the benefits, just because of the higher temperatures, the 750 outlet, for example, you can get much higher efficiency if you choose to use this heat for electricity generation. So you can use the same power turbines and than for, say, the coal or thermal industry, and therefore increase efficiency to the low 40%. And if you then go to a direct cycle, you can probably increase it to 50%. And compared to current large light water reactors, this is where this 20 to 50% increase in efficiency comes. So you can see for the same thermal heat, you can generate more electricity. Because also of the higher temperatures, you can participate in the complete energy market. So not only use the heat for electricity generation, but specifically there's a lot of interest and the potential to use it for process steam for petrochemical industry, specifically in the short term, and the longer term, a lot of interest for hydrogen production. And this is a huge market. I will later show a few examples. Then the HTGRs have this improved safety characteristics, mostly because of the very low power density. It means that after heat or decay heat, after I shut my reactor down, and that this heat can be removed by natural means only, and therefore that things like a core meltdown or massive damage or release of fission products can be excluded. This has other implications, for example, that the emergency planning zone can probably be motivated and shown to be on the site boundary, and that no actions are needed, or specific EPZ can be reduced in size. If we can place these reactors closer to the end user, either being electricity or heat user, you can save things like transmission cost. And also the unique design of the fuel also allow us to go to much higher burn up. So this has been proven, and the designs typically will have a discharge burn up more or less double of current large reactors, and up to quite a multiple of that. And this has been demonstrated in running reactors, but also in tests being conducted in irradiation tests. So, but some of the challenges, of course, because we want to use helium as a coolant and helium as a gas, and a very light gas, we have to have it under very high pressure to get enough heat removal density. Also, since we want to use a low power density, we need quite a large reactor vessel, so a bigger volume of core. And you can see here that for a large high-temperature gas-cooled reactor, shown on the outside, this vessel is probably at least twice as large than a typical large PWR reactor pressure vessel. So this is a challenge. Of course, you can build a smaller high-temperature gas-cooled reactor with a lower power, but this just gives you some idea of the size differences. Of course, also helium is a gas and is therefore non-condensable. So you can't use traditional containment concepts, and therefore need to find other solutions and conventional regulator of different ways and means than the traditional large reactors. And this is not a fact, but in principle, the coated particle fuel is quite complex to make, and even if you make it in very large numbers, you might expect it that the cost of the fuel will be higher than for current reactors. But I think just to emphasize the safety again, this is the main very important feature of high-temperature gas-cooled reactors, and all the designs that's currently being pursued fulfill this requirement. So I have my coated particle fuel. This has specific characteristics to have several layers around the inner part, that's the uranium dioxide or uranium carbide, and or UCO, and then around it a porous buffer layer and 3 different layers. Silicon carbide is one of these dense layers, and their function is to keep most of the fission products under all thinkable conditions within this coated particle that they can't escape. So this is the first principle. And the bottom you can see for different temperatures on the linear scale what the potential release could be, and therefore only at very high temperatures would I expect a large number of these coated particles to fail and to release the fission products or radiation to the core, or ultimately potentially to the atmosphere. So this is a very good fuel performance. Now I need to design a core that can make use of this good characteristics, and therefore I need a typical low power density and a long slender core where my heat removal surface to the outside is quite large compared to my volume, and therefore by all natural means, meaning I don't need my coolant, I don't need the helium, I don't need a pump, I don't need any electricity. Just by natural means I can remove this decay heat from the core to a cooler on the outside that can be a passive, or ultimately even to the building structures without this fuel temperatures going to a temperature that's high enough that I can have significant fission product release. This is shown at the bottom right, where if I lose all my coolant and I don't actively cool, this is typically what a small fraction of my fuel in the reactor might see. Temperature might increase maybe to 1500. If I still have my helium in, then the maximum temperature is much lower. And even if I don't have a cooling system actively working, but have to dump this heat into my building and the surroundings, then you will see a very small effect on the maximum fuel temperature. And therefore you can show with the correct design that you will never reach temperatures where a large amount of fission products can be released. So that's why we say no early or large fission product release is possible. And this is really the main concept, to retain all the radioactivity within the coated particles and the main safety characteristics of this reactor. There's many others, but I think this is enough to emphasize for this presentation. So maybe just to summarize the typical safety terrain for modular HTGRs. So I think the main message is that this fuel failure mechanism of this coated particle fuel are really decoupled and totally independent. It's really depending on your quality of fuel manufacturing and your maximum fuel temperature reached. And in case one of these coated particles may fail, it doesn't affect any of the conditions of the surrounding coated particles. So it's not as if it will lead to a failure of its neighboring coated particle, because it's all driven only by this maximum fuel temperature. Also, a failure of one coated particle won't change how the other coated particles are cooled, because it doesn't influence the cool down path. And if this coated particle fail, the amount of fission products that released are very small, and therefore we need billions of them to fail to have any consequence at all. So this is very important, because it means there's no common mode failure, and there's also no cliff edge effects. So no failure of one coated particle will induce multiple failures of surrounding fuel. So it's not like where if a core meltdown or one pin fail, that the coolability of surrounding pins might be influenced. So there's no common mode failure or cliff edge effects. Okay, so I think this is enough on the safety terrain. I want to look at a few R&D areas and just highlight some of the areas where research and development is being done. But I first thought to just remind you that HTGRs are not new, that high temperature gas-cooled reactors has been built and operated in the past as different projects. Not all of them as modular, fulfilling the design philosophy as I just explained, but using helium as coolant, using coated particle fuels, or in different forms over the years. And the main thing is to say that HTGRs are quite a mature technology with some operating experience. And if the conditions are quite moderate, most of the designers will say no additional research and development is needed. So only if we really want to go to specific applications and specific very high temperatures do we really need new research and development. But of course, A lot of this knowledge are also in danger to be lost, and we need to preserve and transfer this knowledge to the new generation. Also, we have to make sure that the SMR designers or the current designers do actually know and implement the lessons learned from these previous programs. So that's very important. Okay, but then some of the areas that some research and development work is being done. For example, KIF have working areas on materials, components, and supply chain. On the fuel, mostly advanced fuel, the fuel cycle and waste minimization, the design and system integration, cost reduction approaches, safety demonstration, licensing, code generation that I already mentioned, and energy system integration. You'll see for the IEA, similar areas were identified, fuel again, and the fuel performance. On materials, graphite, new graphites need to be developed. Many of the old graphites is no longer available. For high temperatures, we need new high temperature metals, software development, code development, verification validation is very important. The requirements for safety standards have changed over the years, also for codes to be verified and validated. The safety, the design and other safety requirements very specifically has to be interpreted for modular high temperature gas-cooled reactors, and that's another area work is needed. Then on code generation applications and the economy of these reactors, and finally on experimental facilities for verification, validation, and also for demonstration tests that might be required for licensing. So this is some of the areas that the IEA has been working in the past. So very short, some of the latest information, and this is not comprehensive, but gives you some idea of the work that's been done. So over the years, many of the member states has been working on coated particle fuel, initially Germany and the US, but also work been done in Japan and more recently in China, but also in Korea, South Africa, and Indonesia has been looking at the fuel, for example. So you can see how this envelope of the fuel has been expanded over the years. Of course, this is dependent on your application. You won't go and test your fuel to very high burnup if you don't intend to use very high burnup in your reactor. So I will say in each program, it was really tested for fit for purpose has been applied. But you can see that over the years, it has been expanded in different temperatures, higher temperatures, higher burnup, higher fast fluences, and so on. Then on the one example of the retention capabilities of this fuel, also the improvements over the years and different techniques. You can see this is a log scale, 10 to the minus 1 to 10 to the minus 10. And some of the radiation experiments are being shown here. And the typical release of one of the isotopes, krypton-85, the R/B ratio. And you can see how this varied, but the good news is over here this has reduced, and the latest fuel are really very low release fractions. Also things like the free uranium loading or contaminants within the fuel has really decreased as we have modern quality assurance and modern manufacturing techniques. So this is very good news. So even the experience from fuel should be orders of magnitude better than the initial experience in the 60s to the 80s. Graphite I mentioned, there's information on graphite, for example, at the agency in the graphic knowledge base. New graphites need to be irradiated and understood. There's also the development of new high alloy metallics, for example, alloy 617. So new materials that needs to be developed to support future applications. On the software development, benchmarking, VMVs, this is some of the previous activities the IEA has done. Recently, we also started a repository or like a database on all the experimental facilities and HTGRs. So this was initiative started and to be completed. but to share information for member states if they're interested. Where can they find experimental facilities? What data is available, specifically if you want to do verification and validation. Then this is actually very good news, that recent development, that the research center Jülich, that's very well known for the codes VSOP and Tinte and others that they developed over many decades. They unfortunately, due to the close of the German nuclear program in general, they worked on HTGRs has stopped some years ago, but the last few years before they really stopped the work, they've been actively developing a new code system called HCP. That's really modern multi-physics, multi-module code that really replace all the old codes, VSOP, Tinte, and others. This code system and a large archive of information has been released to the IAEA for free distribution to all interested member states. Together with the HCP code, also the VSOP 9911, so the latest VSOP, and the fuel performance code Stacy has been released, and I put the current status here. So as we received, and we already received it, the VSOP 99 is really ready for distribution soon. It's a mature code with good manuals and so on. Stacy needs a bit of work on the documentation, then that can be released as a standalone module. And then HCP that really replaced Stacy as a module with HCP, and other modules replace VSOP and Tinte. This needs some further development, but we hope to do this. We plan to do this under the IAEA open source nuclear code reactor analysis initiative called ENCORE. And within the next few weeks, hopefully we can release VSOP, and then to be followed by Stacy and HCP after some additional work has been done, really to harmonize different research versions of HCP. But this is ongoing work. But the main message is that these codes has been released to the IAEA and will soon be available for distribution and for cooperation and further development. So this is very important. And this HCP is really a modern code that can be further developed to really becomes the main code system for high temperature gas-cooled reactors in future. Safety requirements, I'm not going to say too much about this, just to, I think a lot of work has been done to look at the current requirements and see if it's applicable or how it can be changed. We had a coordinated research project on this, and the document of this needs to be finalized. There's also within the nuclear safety department some activities and even new initiatives to look at all the different regulations and guidance and documents of the IAEA and see if they're applicable to small modular reactors and high temperature gas cooled reactors, for example. There's also a new initiative that the agency is the secretariat for on the SMR Regulators Forum. And I think if you just go and search on the many actions taken by regulators, for example, in the US, to develop new regulations or new licensing guidance on how to license non-water-cooled reactors with a specific release for high-temperature gas-cooled reactors. You will see some of the reactors in Canada that are being licensed as high-temperature gas-cooled reactors. I know UK have done some work. So a lot of new and better understanding of the safety case for high-temperature gas-cooled reactors at the IAEA, but also in many of the member states. Cogeneration, I mentioned this. This is really not only to sell electricity, but have other products also available, and also the flexibility maybe to switch between this. This becomes very important in a new market where load follow is very important for on the electricity grid, and also in times where renewables, for example, make a lot of power to be able to sell your heat for, say, hydrogen production or for another process that needs it. So, of course, you have to look at the economic feasibility of this. You have to look at the safety and licensing and how to sell the different products. But this is really a huge potential for high-temperature gas-cooled reactors. So a bit of the activities of IAEA. I see I need to speed up a bit. The IAEA keep a database of advanced reactor information system, and this recently we updated 11 SMR designs within this database, and there's quite a number of high-temperature gas-cooled reactors included if you want more information. And then also for small modular reactors, every 2 years the agency publish what we call a booklet, but this is more becomes like a real quite a substantial document. And the latest release we have 72 SMR and microreactors designs, including high-temperature gas-cooled reactors as always. So this will be printed this week and should be available also on the web shortly under the ARIS database. This is some of the examples of the designs I will make later. HTRPM was mentioned. Also the, for example, in US X Energy, the XE100 reactor is under development and should start with licensing activities next year. From Japan, the GT-HTR, and also the Framatome US design on a direct cycle large prismatic reactor. So different examples of reactors under development. Here's the HTRPM status, some photos that was supplied by INET. As you heard already in the previous webinar, also in Indonesia, operations are expected in 2021. And just a few pictures of the site, the construction, and some of the components within the reactor. Then something new that's been got our attention, the agency. There's a lot of interest in so-called microreactors. We still have to define it in detail, but this is reactors smaller than 10 megawatt electric. This is how we currently define them. But they might have other specific characteristics and niche applications. Just to say, many of them or some of them is also high-temperature gas-cooled reactors. Here's 3 examples. One of them is a high-temperature gas-cooled reactor. And then also making good progress, for example, the MMR design from Ultra-Safe Nuclear Corporation, together with Global First Power and Ontario Power Generation in Canada, have made application to build a reactor in Canada and is currently busy with the environment assessment. So also in this area, good progress has been made with specific niche applications of these microreactors. That's quite exciting. Then the agency, all 4 these projects has basically been completed. So just for information that the documents should be available in the foreseeable future. Some work on irradiated graphite, some work on the uncertainties in the analysis of high-temperature gas-cooled reactors. I've mentioned this, looking at the safety design criteria of reactors and how it can be applied to modular high-temperature gas-cooled reactors. And then one project that we cooperated with another division on how we can use the process heat to extract mineral products. This was completed in 2019 and the tech doc has been finalized. So this is some of the information you might expect from the agency soon. And then a new project to be started maybe late this year or early next year on technologies to enhance the competitiveness and early deployment of high-temperature gas-cooled reactors and small modular reactors. So there's a lot of ideas on how to use different power conversion units, maybe how to do load follow. So what technologies, innovations are available to really make these reactors more attractive in future. So then a few slides just on flexible application. Of course, we know due to the high outlet temperatures I mentioned, there's a real potential for high-temperature gas-cooled reactors. You can see it's the highest of all the different types being pursued or as small modular reactors. And Therefore, we could look at different applications, process heat applications. We can do load follow more efficiently by switching between different applications. Maybe some of the waste heat we can use for desalination. So this whole idea of different applications being pursued by small modular reactors and HTR specifically. And we also have a tech talk under development on the options to enhance energy supply security using hybrid energy systems that includes SMRs, then together with renewables. And here's also some of the process heat applications that can be pursued together to do, for example, load follow to support the intermittent renewables that we know is being more and more deployed by member states on their electricity grids. And this is just to show how different coupling examples, how heat can be extracted, or different power conversion systems or models that can be used to support load follow and switching between different applications for high-temperature gas-cooled reactors. Okay, then finally, a bit of what's happening in the member states. Just have one slide on this, and then I will highlight only a few things on what we did in Indonesia. I have quite a number of slides, but I think you can look through it for reference later on. So first of all, I mentioned the MMR reactor that's for the Chalk River site in Ontario that's busy with a license application and the site environment impact assessment. Also in Canada, there's other two small HTRs or microreactors that's also been with the pre-licensing stages talking to the regulator. So so at least 3 small high-temperature gas-cooled reactors busy in Canada, so very active there. In China, we know about the HTGR that should start operation next year, but also to mention that they already have a design with 6 reactors called HTGR 600 that is under development, and several sites is under consideration to build this as the full-size modular application they want to apply in China. In UK recently, we learned about the allocation of money for the U battery, and this is part of the support of advanced non-water-cooled small modular reactors. I mentioned in the USA, X-Energy has been developing a Pebble type high-temperature gas-cooled reactor, and they plan to start the licensing in 2021. Also, there's quite a lot of funding for other activities related to high-temperature gas-cooled reactors, for example, to develop price of fuel or to develop the higher enrichment LEU, so the high assay LEU that they talk in the US about. It just means enrichment between 5 and 19.75%. Indonesia, we know Indonesia has been working on the RDE, HTR type reactor with experimental reactor for 10 megawatt for the last few years. And also the siting that they did at the Serpong site. And I will tell you more about the expert missions. Jordan also is interested in SMRs, and they have narrowed down the number of designs to 4 to 5, and 2 of these designs are actually high-temperature gas-cooled reactors. Michael mentioned Poland. I will say a bit more about Poland, what they plan, but also they plan to build a 10 megawatt experimental HTR possibly in future. And this now is maybe not so highly pursued anymore, but in Saudi Arabia, they did a feasibility study for high-temperature gas-cooled reactors to provide process heat for the petrochemical industry. Okay, so this is just some of the activities. I'm sure I left out a few. Maybe just something on Poland. So they need to replace some of the coal boilers in future to reduce their environmental footprint. And they are doing studies on replacing these with high-temperature gas-cooled reactors. Moderate temperatures that they need, so you see 400 to 550. And they foresee that they might need at least 10 reactors for Poland alone of the size of 165 megawatt thermal was determined as the optimum size. But also in the studies, they saw huge potential also outside of Poland. And here, some of the from the ministry, some of the benefits that they highlighted that you can have a look at. So decreased dependence on fossil fuel, price regulation, so to know what the price would be, high added value, and to boost the economy growth. Also, they plan to deploy large light-water reactors for electricity generation. So this will be complementary only for process heat, and they also see a large export potential. So then for Indonesia, this really, at least what I'm aware of, this started in September 2013, so now really 6-7 years ago, with a first visit to look at the R&D program, and been done within Batam on high-temperature gas-cooled reactors, and then the possible deployment of a small experimental reactor was discussed. This was followed up by a letter that was sent to our then DGG of Nuclear Energy, and a follow-up visit in 2014. As I said, I'm just going quickly to go through this. Then the TC support started mainly in 2015, the technical support. There was things on HTGR technology and safety, hands-on training on the different codes. So the predecessor of VSOP 99, VSOP 94, and the Flonix code that's used for HTGR analysis. Also later on, one of the IAEA training courses was held and kindly hosted by Batam. Also missions on the HTGR fuel engineering, the coated particles, quite a few missions supporting the fuel, how it's made, what procedures should be in place, what quality assurance should be in place, how the kernel manufacturing is done, and then several missions also looking at the experimental power reactor, evaluating the PSAR that was available, and later this was expanded to look at the additional design work that has been pursued by Batam. Also, Babaten was preparing for the license application, and from their own funds implemented quite a number of activities, scientific visits, looking at different codes, looking at the fuel manufacturing experience, for example. As I said, then follow-up of the RDE design, looking at the updated design and work, and start of basic engineering work being performed by Batam. Also, but Babaten already had expert missions on the HEP code, the second one already in 2017, and also look at safety classification, quality codes and standards. So both Batam and Babaten having several missions to improve their knowledge through the support of the agency. Again, on the RDE design support, Babaten had an expert mission on this phenomena identification ranking table and how to use this to facilitate regulatory review. Again, they will also went to Korea to look at their code systems, for example. So you can see all the themes that has been addressed in R&D also been covered by the TC support to Indonesia. And then we were also happy to support and to participate in some of the international conferences within Indonesia. So more recently, there were some plans already drawn up earlier this year to how to support Batam and Babaten throughout this year. But as we know, all of these plans has been postponed or put on hold, and we will have to reevaluate how we can support Indonesia in future. But the good news is the conference, in cooperation with the HTGR conference, is planned for next year, and also the year afterwards, the International Nuclear Graphite Expert Meeting is also planned to be hosted within Indonesia. So thank you for your attention. Hopefully this gives you a good overview of what the agency has been doing in support of HTGRs in all member states but also specifically within how we supported Indonesia in the last few years. Thank you very much.
Thanks a lot, Frederick. It's very clear, interesting presentation as well. We've got a lot of information from you technically and about the current status of HTR as well. Before we move on to the discussion, I would like to acknowledge and thanks to that HTR 2021 is organized in cooperation with the IAEA. We are pleased here that Mr. Hadid Subhi, who is here today with us, has been appointed as the representative of the IAEA, and he's also a track leader for the track 1, together with Frederick Ritzma and Ms. Geniri Nasunario. And we have many questions here. I'm not really sure time is enough or not to discuss or to answer all the questions. Mostly for Frederick. The first question here from Pa Alfano. He asks about a small modular reactor development refers to the first nuclear reactor used for the U.S. naval submarines. He said that USS Nautilus, 1955. Is that correct? Sort of like that. And he asked it because he could imagine that the reactor in that submarine wasn't as similar, common or regular nuclear power plant.
Yes, so maybe
comment about this. Yep.
Just a short comment. A lot of the reactors was first developed as small reactors and later increased in power and size. I think what's different in the small modular reactors is a re-look at the design philosophy. So especially on the safety, and this is not only for HTGRs, but for all the different small modular reactors, a real emphasis on the safety characteristics of these reactors. I will say the initial reactors rely on active safety alone. In the small modular reactors, the philosophy is to also rely on passive safety features and also other design features that doesn't require electricity and active systems. But yes, you will also see the small modular reactors and small and medium-sized reactor project of the agency. It's not new, it's been there in the 1970s, but I think that's a distinction between the initial reactors that are really only small versus what we look at today as small modular reactors.
Okay, thanks a lot, Frederick. It's again another question for you as well from Ms. Maya Dewi. She asked about what is the constraint for the application of small modular reactor development? I think you mentioned it in the presentation, I think. Yep.
I think the main thing is we need demonstration and we need to know what the cost of these reactors would be. So the main thing is you don't know until you have built and operated, then you have real knowledge. So until we don't, and we know the first floating reactor has been deployed in Russia, the first HTGR should be deployed next year, and that will give us the knowledge and show the viability.
Oke, thanks. Mudah-mudahan Bu Maya bisa menyimak ya. The third question is from Pak Topan. This one is very interesting, I think. He asks about the current status of the Poland HTR program. Fortunately, we have Professor Godowski here. I think he's attended this webinar as well. How is the current status of Poland HTR program? How other EU countries contribute to it? Is there opportunity for non-EU countries to collaborate?
Okay.
Yeah, Professor, yes. Hand over the question. The answer for you.
Yes, can you hear me? Yes.
Well, yes, very clear.
I understand the origin of that question apart from curiosity, namely very few weeks ago, the Polish government announced the proposition of the nuclear program development, which is based on the about 6 gigawatt electric PWRs. In the same program, there is a provision for the research reactor in HTGR, But this proposition creates a lot of turmoil, I would say, and there is a pretty large concern at both expert community that putting all the eggs in one basket is not a very good idea. But the good thing that the program appeared, it's pretty aggressive, by the way. The only thing which we are worrying is that if it will not slow down the research on HTGR. So we hope that we can find a very good, I would say, synergetic solution for both. This program is not yet decided. It is under discussion with the expert community, and we are putting very strong concerns that as I said, PWR technology will be 50 years old. So one should at least think about, for the first, combined power and heat generation. I mean, in my private opinion, no reactor should be built today without combined power and heat. So I dislike this program very much because of its 50 years old philosophy. You know, focus on electricity, don't bother about anything else. This is not the philosophy of the 21st century. So I would gladly support, you know, even development, very aggressive development of LWRs or PWRs, if it would be actually also using heat from those reactors. And that's a problem because this is a huge heat generator, so you have to have the consumer. That is another argument for small modular reactors. Because, you know, if you want to use the heat, I mean, from one big electricity generating reactor, you will have problems to find really good consumer and customers for this tremendous amount from 2 or 3 gigawatt thermal of heat. So this is another strong argument. Go towards SMR more aggressively and more dynamically.
Thanks a lot, Professor. Pak Topan? Clear? Okay with the answer?
I also answer in the chat. So if anybody wants to have more, if anybody wants to have more information, do not hesitate. There is my email. Do not hesitate to contact me. I will explain also where we are. But our research program is untouched. We are going towards the research HTGR reactor at National Center for Nuclear Research.
Okay, thanks a lot, Professor. Bapak Ibu nanti mungkin bisa kontak Profesor Pak Topan, bisa kontak, you may contact Professor Kodowski perhaps for further collaboration between Indonesia, perhaps with the Poland or with other countries interested with the HTR technology. Let's move on to the 4 questions from Pak Susilo Widodo. Pak Susilo mau menyampaikan langsung? Okay, I will read it, I think. In Indonesia, NPP is classified, it's for RITSMA actually, again for it. In Indonesia, NPP is classified as new energy source, while solar, wind, hydro are classified as renewable energy sources. You may be surprised by this classification, as in fact, nuclear energy is not really new energy. It is new in my country, but it has been operated for more than 50 years in many countries. I argue that nuclear energy is not new and even theoretically could be renewable. You think that HTGR or SMR technology in the future will be able to support my arguments? That's a question from Susilo. Is the chairman actually for Indonesian nuclear communities?
Yeah, I can answer maybe that. That's an interesting thought. I think the whole what is renewable is. I think there's more discussion needed on this, because it's true that the energy source is renewable, and I mean the sun is shining, the wind is blowing. But if you look at the whole cycle and the materials needed and recycling of that material, even the renewables need to maybe more carefully think about. The whole cycle within the renewable energy community. I know people that looking at the thorium cycle or fast reactors have the argument that maybe nuclear could be renewable. I think it's more important for us to focus on the benefits, also the on-demand availability of nuclear. And although it's not a new technology, it will be new to Indonesia. So I understand why it was classified under new for Indonesia. But I think we should emphasize the availability on demand and also how it can support renewables that currently do not have the storage capability and is intermittent and needs some backup. I think that's where we need to focus our efforts.
Thanks a lot, Risma. Another question here, again for you. In connection with the climate change, Indonesia needs nuclear power plants that are free emissions. Do you think the price of electricity for HTGR as an energy transition can compete with the coal? I think, yes, it's about the price actually. We have another participants here actually from China, Sun Jun. Maybe he can add the comment after you, I think, after Ritzman.
Yeah, I think that's why I said we still need to deploy these reactors and really determine the cost. It also, as we know, depending on which country, I know many countries look at carbon costs if they want to try and calculate the cost or want to include aspects of costs to the environment. It also really depends how the future international trade relations will change. At some stage, I was really thinking that some countries will put restrictions on import from countries who does not reduce their carbon footprint, and then the cost becomes irrelevant. It's if you can't supply CO2-free electricity, then you can't compete, and then the price becomes irrelevant because it's then survival. So I don't think we know that answer yet. I think the HTR designers and China won't have built the reactor if they don't think it can compete. I've seen some of the cost estimations of a kind HTRPM, and then they do compare it with other nuclear. But as we know, the price of coal generation and nuclear generation varies by quite a large margin in different countries. So it's very difficult. It's really a country-specific question to be answered in the end.
Okay, thanks a lot, Risma. Another question, I think it's a bit political, this one. Do you think, from the participant, SOG, I'm not really sure, is that correct? Do you think HTGR can convince the US to let the coal die and preferably leave fossil fuel completely? I know everyone plays a part in changing the climate, but I'm particularly concerned about the US because it's such huge force and there's a way too many anti-science folks there. Yeah, sort of like that. It's about a bit more political, I think.
If I it's as you say, it's difficult for me to react, but personal opinion is the real competition is gas and will be gas for a long time, because already the reduction in CO2 from coal to gas is significant. But I think as it's also a two-party system and two different people campaigning for coal and against coal. So I'm not sure if HTRs as such will really change the perceptions, but I hope that some application and the carbon-free contribution of nuclear will be more acknowledged throughout the world and also in the US.
Thanks a lot, Ritzman. Another question, it's from Ari Nugroho, it's from Batans. It's about the HTRPM actually. Again, perhaps our colleague from China maybe, Dr. Sun Jun, may add the answer as well. What is the main issue in the commissioning of HTRPM? Because it has been postponed frequently.
Dr. Sun Jun, could you
please unmute
your microphone? You can unmute by yourself. No.
Dr. Sunjun, would you like to?
It doesn't respond.
Okay, he doesn't respond. Okay, maybe from Ritzman, perhaps.
Of course, this is not first-hand knowledge.
Okay.
I know there's a challenge on the steam generators that was installed later on, and some rework had to be done on the steam generators after inspection, and I think that delayed the start of commissioning. So my impression is that the commissioning, I think also my slide I made note that it only started very recently. So I think this was more still the final sign-off and installation of some of the components. And the main delay there was, I will say, first of a kind, different design of steam generator. And it was really about the specific, because it has these 19 modules and the specific way how these 19 modules get coupled at the top and the bottom to actually have a single inlet and outlet. So that design and that manufacturing and quality of that, there had to be some rework done on the steam generators. So according to the latest information that Professor Sun gave you in the webinar, the commissioning only started in September this year.
Okay, thanks a lot. I think hopefully that's answer the question from Pak Ari, Pak ya. And I think the final one is one from Mr. Ardat. Dear Dr. Frederick, what is your opinion about using microreactor technology as the main power for space travel?
Yeah, I think in the space reactors, there's been a lot of work been done in the past. I'm not expert on this. So I think the microreactors are really focused on niche applications for mines in or on islands or for the northern territories of Canada. So the previous space applications has always been for satellites and so on, either been only heat sources or even smaller reactors. So I think that's in a different domain. It's clear for me that it will need to be used. If you go further than Earth, then the solar radiation just becomes less and less. And so there's quite a lot of development in that area. But till date, the agency has not been involved in the space reactors.
Okay, thanks a lot, Ritzma. Okay, that's all the question, mostly for Ritzma. And thanks again for all the participants for the questions. Again, we are very grateful and thanks to the IAEA to support this webinar as well as for the conference. Before we close this webinar, we still have some, we still have a closing from Pak Jarod. If you would like to talk about perhaps the seminar venue, for example, Pak Jarod.
I would like to ask Michael to give some speech. I think like a closing speech. After that, I will talk some information for the second webinar. Please, Michael. You can unmute.
Oh, now it.
Yeah. Sorry.
Okay. Well, I have to disappoint you. I will not hold a closure speech. On the contrary, I hope I will be able to hold an introduction speech. Maybe at the next seminar, maybe talking about a specific topic which is of my competence. So I can offer you, for example, some insights into process heat market questions and applications. So we have some very new and I think powerful results from international studies there that might be of interest and might attract actually people also to the conference. And yes, I would prefer to look forward and to go into an introduction instead of closing this year. Yeah, I'm very happy that this has worked out so well. And I think also from the questions, I can see that many people are participating who have thought about the subject already very thoroughly. There's still a long way to go, especially for Indonesia, but I'm very confident that together we can go well, at least some of the way together and participate in common projects. So thank you for the opportunity to participate here, and I hope it will not be the last time. Again, I offer you some more input for the next one. Thank you.
Yeah, thank you very much, Michael. Well, thank you for the closing remarks. This is the first webinar, so it means we will have the second webinar this year, maybe in November. So we will try to give the thema a good and interesting thema. So again, I would like to thanks to the speakers, Michael Futter and to Frederick Ritzma, because they give very excellent presentations. And well, for Frederick, because you help us very much, well, I would like to say thank you. We will miss you. Hopefully you will success in the next step, next challenge. And well, we hope you are still in our community circulations on the HTGR community. Again, thank you very much. And thank you for all of our audience. In the peak time, the audience was 200, more than 200, and in YouTube more than 30 people attend this meeting. It's very excellent meeting. So we will find a good theme also, because the audience, they are very curious. The questions talking about the space station or something like micro reactors or something, the submarine and other. So that's why these webinars not only talking about specific issues, but also the general issue on nuclear energy. Thank you again. Thank you very much, and good night, good evening, good afternoon. Bye bye. See you next time. Thank you.
Bye. Thanks, Pak Jarod, for the closing. With that, we conclude the webinar. Thanks for the.
Please unmute, please, Pak Saiful. Please unmute.
Okay. With that, thank you. With that, we conclude the webinar. Thank you very much for the participants all, and especially for the speakers, Frederick and Mark Futter. See you next time in the next webinar. Hopefully we can join the HTR 2021 as well next time, next year. Thanks again from me.
Terima kasih semua.
Thank you.
Thank you. Pak, ada Pak Suryantoro.
Thank you.
Iya,
Pak
Pak
Sur.
Arin.
Terima kasih.
Thank you, Prof.
Pak
Jarod.
Sal Mustafa.
Selamat malam, Pak Jarod.
Selamat malam.
Thank you.
Terima
Pak
kasih.
Jarod.
Terima kasih.
Prisma.
Thank you. Next week, we will invite the CARM 25 from Argentina. The speaker is Mr. Dario. He's expert on the CARM 25, CARM 25. Moga-moga menarik sekali perkembangan teknologi di Argentina. Moga-moga Bapak Ibu sekalian masih berkenan untuk hadir mengikuti webinar tersebut hari Kamis tanggal 17.
Thank you.
Ya.
Siap mendengarkan.
Ya,
Siap.
terima kasih.
Terima kasih Pak Jarod.
Sami-sami.
Terima kasih. Selamat malam. Selamat malam.
Terima kasih. Ada Pak Hadi juga kan di sini.
Terima kasih Pak
Selamat
Jarod.
malam.
Thank you, Frederick.
Di kantor
Komplit. Pak Sur. Assalamualaikum Pak Sur.
Pak Hadi.
Alhamdulillah. Gak pakai video ini.
Iya.
Oh, dia. Sarungan soalnya, Pak.
Sarungan soalnya Pak Sur.
Iya, sambil digigit nyamuk di luar ini.
Ada Pak.
Ya, saya pamit dulu. Mari Pak Saiful.
Mari.
Terima kasih Pak Jarod.
Bye. Thank you, Frederick. See you next time.
Thank you, Frederick.
Thanks Frederick.
Thank you, Risma. Ya, assalamualaikum semua.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Oke, sehat.
Waalaikumsalam.
Waalaikumsalam.